this is going on page 27 when we're done. So we reviewed factoring because we got to be able to do it to do this stuff. We're going to talk about polynomial functions and complex zeros. So what's another word for zeros? What else we got? Solutions, x-intercepts, roots. Good. Roots, solutions, x-intercepts, zeros. They all mean the same thing, right? Officially, you write the answers differently. Like if I'm asked for an intercept, then usually that means you want an ordered pair. If I'm asked for a zero, that usually means you want x equals 3 or something like that. Okay, so zeros of polynomial functions. I'm going to flip try something weird. Here we go. So we understand what zeros are. That's not a brand new thing. This says, given a polynomial function, p of x, whatever that is, if p of a equals 0, then a is a 0 or root of p of x. What that is saying is this. Here's just a simple little quadratic. Let's pretend like this is at 3. So if this is p of x, p of 3 is 0, that means 3 is a 0. That's what those words mean, okay? If a, so a is my 3, if a is a real number, which are the only ones we can actually graph, then if x equals a is a 0, because here x equals 3 would be a 0, then x minus a, or x minus 3, would be a linear factor of p. And it is a linear factor because x minus 3 is like an equation of a little line, all right? So when we factored all of this, right here I have 1, 2, 3, 4 linear factors. That's what we're saying, okay? Even this guy here, this guy is also a linear factor, by the way, because 0 is still important. All right. So those are zeros. Again, just kind of a formal definition of something we've already understood. I'm sure that you have seen repeated zeros. I don't know that you've officially used the term multiplicity. If a 0 happens more than once, okay, it could be a double root, a triple root, something like that, then it has multiplicity, right? Fancy word, doesn't really mean anything fancy. But so if I have this linear factor x minus a, if it's repeated n times, then the corresponding 0 has a multiplicity of n. And don't worry, I will explain that a little bit better. But again, we have to have official words sometimes. All right, so it says typically we know that the graph of a polynomial passes through, and this should be a bigger blank. I apologize. Oh, I'm not spelling it right. It's a long word, and I didn't give you very much space. Through, passes through the zeros. So right here I pass through that 0, and then I pass through that 0, just whoop, right through the axis, right? Then it says, however, when a 0 has multiplicity greater than 1, the graph will behave differently near the 0. Okay, so that's one thing that we're looking at now. Not just, hey, these are zeros, but what do we know about these zeros? How many are there? So forth and so on. So look at this graph over here. We've got, and here's this function. Bless you. It's graph to the right. It says, notice the behavior around the zeros. So that means this, I have a 0 at -4, I have one at -1, and I have one at 3. Those are my 3 zeros of my function. For 4, -4, it just passes straight through, kind of like our quadratic did. Here at -1, it does this little wiggle, all right? And then here at 3, it bounces off the axis and comes back down. So let's talk about this wiggle a little bit. This function has 2 relative maximums, one right here and one right here. There's not a maximum or a minimum right there, okay? Because remember, maximums and minimums occur when you change from increasing to decreasing or vice versa, right? Right here, the function is decreasing and it wiggles, but it stays decreasing the entire time. That is a point of inflection. Remember how the cubic, that was like your first introduction to a point of inflection? That's a point of inflection. Don't try to force it into a maximum or minimum, okay? Because there's one of those on that assignment from 1-4, I think, and I think there was some confusion about that, so just want to make sure you understand that part. Okay, so notice here that when it passes through the boring way, x plus 4 there's not an exponent on my factor. At the point of inflection, I have an exponent, and at the bounce, I have an exponent. Okay, so now we have to kind of know what these exponents are doing. So the multiplicity is the degree of its factor. So for this function here, this x plus 4 gives me just a negative 4 as an x. That makes sense. This gives me a negative 1, but because of this, I have negative 1 with multiplicity 3. This gives me positive 3, but because of this, I have 3 with a multiplicity of 2. Does that make sense to you? And again, those multiplicities are going to tell us different things. So it goes on to say, at x equals 3, the multiplicity is 2. Okay, that's over there at that bounce. The graph of the polynomial is tangent, that's our official word, to the x-axis, or we think about it bouncing off, because it does look like a bounce, that's why we talk about it that way, but it's tangent. The x-axis in this neighborhood only intersects the graph at that one point. Okay, so that line is tangent to that. The graph, so here's our general rule. The graph of a polynomial will always be tangent to the x-axis at any 0 with an even multiplicity. So it doesn't have to be 2. It can be 2, 4, 6, 8, 10, 12, whatever. Now, one thing that is not mentioned here, and I haven't found it mentioned anywhere that we're required to talk about it in this course, but I'm going to bring it up anyway, is that when you have a multiplicity that is odd but greater than 1, that is when your point of inflection happens, okay? So there is still something happening when you have an odd multiplicity that's greater than 1. It's just not the bounce, but the bounce is what we're most concerned with. Does that make sense to you? So we don't have to necessarily know that. All right, so then how are we going to be asked some of this stuff? It says for each of the polynomials, determine the degree of the polynomial. What is the degree? And find all the real zeros and state the multiplicities. All right, so when I look at A is already all factored for me. I have 3 linear factors, so I know it's completely factored. I need the degree. I don't have to multiply it all the way out to figure out the degree, but if I did multiply it all out, what would the degree be? Well, when I square this, I get x squared, right? Times x gives me what? X cubed. X cubed times x cubed is x to the 6. The degree is 6. Then I got to have my zeros. X equals. Well, what is this 0? 0. And it has a multiplicity of what? 3. And then this is just negative 1. And he doesn't have a multiplicity. This is 4 with a multiplicity. Oh, I left out the L. Multiplicity. Oh, now my board's being weird. Multiplicity of 2. What questions you got? We good on that? All right. So look at B. Is B completely factored? No. This is a linear factor. This is not, right? But I can figure out the degree before we do that, before or after. It doesn't really matter. What is the degree of this polynomial going to be? This will give me x to the what? 4th times x squared gives me 6. And then I need to factor that. So g of x equals 3 times x plus 2 times x minus 2 times x minus 2 to the 4th. What do you notice? Yeah, the x minus 2's, right? So I need to combine those. So one more step here, g of x is equal to 3 times x plus 2 times x minus 2 to what power? The 5th. So just clean it up a little bit. Everybody good with that? All right, so then that means my zeros are at x equals, does he give me a 0? No, because there's no variable. This gives me a negative 2 with no multiplicity. This gives me a positive 2 with a multiplicity of 5. Okay. What questions you got? We good? I'll take that as a yes. All right, C, what is our degree here? What do you think? What's x squared times x to the third? X to the fifth, right? You add your exponents. Then I have to factor. So in that first one, do I have a GCF? Yes, it is x. So that is x squared minus x minus 6. There is no GCF in the second one, and a is 1, so I can go ahead and factor it into two binomials. And this is x and x. The 12 is positive, so the signs are the same. This is negative, so they're both negative. What are my two numbers? 3 and 4. Good. All right, so now I got to factor that piece. So y is equal to x times, now a is 1, so I can make that into two binomials. X and x. 6 is negative, so the signs are opposite. What are my two numbers? Negative 3 and 2. Very good. Okay, and then I still have x minus 3 and x minus 4. Now, can I clean this up a little bit? Yes, I can. Y equals x times x plus 2 times x minus 3 to what power? 2 times x minus 4. Okay. So then x equals, what does this guy give me? 0. Then that gives me negative 2. That gives me 3 with a multiplicity of what? 2. And then this gives me 4. What questions do you have? Okie dokie. Good deal. So just extending your understanding of zeros and factoring and all that good kind of stuff. All right, so now we're going to talk about complex roots. We did find some on the factoring stuff that we just finished. So here's a kind of a reminder. Some polynomials, some, not all, have roots that contain an imaginary number. That means you will not see them on the graph. They don't show up as actual zeros. This function is x squared plus 1. This is one of those where you don't get, it's not that you get 0 answers, you get 0 real answers. When you go to find the zeros, you set that equal to 0, so you get x squared equals negative 1. And then when you take the square root, you have to add the plus or minus, and you get 2 of them, right? And then you get plus or minus I in that particular case. Okay, so this is kind of a reminder of what happens with those imaginary roots, that they're not actually crossing the x-axis. There's a different way to look at it that we're not going to talk about right now. But one thing I want to make sure you understand is they always come in pairs, okay? When I take the square root, it's going to be a plus or minus. They have to come in pairs. That's one of the things that you're going to be asked about. So let's flip this over and talk about that. So all imaginary roots come in pairs, like I just said. Hopefully you understand why. So if a plus bi is a root, then so is a minus bi. The sign changes on the I part, not on the, or on the bi part, not the a part. So these are called conjugate pairs, which I know you talked about in Algebra 2 with imaginary numbers and with square roots. So you might have like 2 plus the square root of 3, so you have 2 minus the square root of 3, something like that. So we're going to determine the conjugate of the following complex numbers. If 4i exists, then negative 4i has to exist, right? That's its conjugate pair. So B, I have negative I. What's its conjugate pair? I. C, I have 2 minus 3i, which means I also have 2 plus 3i. D, I have negative 4 plus 2i, which means I also have negative 4 minus 2i. Notice you're only changing the sign on the I part, not the other part if there's another part. Easy enough? They come in pairs. So how are you going to be asked about this? Well, we've got the fundamental theorem of algebra here that says a polynomial of degree n has exactly n complex zeros when counting multiplicity. Now, the complex numbers might not have talked about complex numbers until you got to imaginary numbers, and they're not one and the same. Because complex numbers can be written in the form a plus or minus bi, right? That's what makes it a complex number. But that means I could write this as 5 plus 0i, which isn't that just 5? So 5 is a complex number. So imaginary numbers and real numbers live in the complex number system. That's why it says that's how many zeros I have, period. Whether they're imaginary or real, that's how many zeros I have. If it's to the 4th power, I have 4 zeros. Some of them might be imaginary, some of them might have multiplicities, but that's the way it works, okay? So here's one way you can be pretty confident you're going to get a question, something similar to this one. It says the graph of the polynomial function, f of x, is shown in the figure above. It is known that x equals I times the square root of 3 is a 0 of f. If f has degree n, what is the least possible value of n? So without having more information, I can't give you exactly what n is, but I can give you the least possible value of what it would be. On my graph, how many zeros do you see on the graph? 2. So I have this one here, and I have this one. You agree with that? Tell me something about this 0. How's it different? Yeah, this one goes through and this one doesn't. It bounces, and if it bounces, what do we know has to be true about the multiplicity? You can flip it over and look if you got to. What do you know is true? It has to be even, right? Right here. Ooh, where'd it go? Here we go. The graph of a polynomial will always be tangent to the x-axis at any 0 with an even multiplicity. So I don't know what the multiplicity is here at -1, but I know it has to be even. So it can't be 1, can't be 3, it's got to be 2, 4, 6, 8, something like that. So I have an even multiplicity here, and that's just a plain old pass-through, so that's just 1, right? So let's list out, I know it doesn't ask us for this, but let's list out what our zeros are, okay? So I've got x equals, starting here at -1, and I know that that multiplicity is even. I don't know what the number is, but it's even, and that's going to help me in just a minute, okay? Then I have here at 3, and that's just a single one, right? They told me I have I times the square root of 3. So what else do I have to have? -I square root of 3, right? So if I think about what's the least possible value of n, what's the least number of actual zeros I have, real or imaginary, I can count up 1, 2, 3, right? What's the smallest multiplicity this can have? 2, because it has to be 2 or 4 or 6, and I don't know what, but the smallest it could possibly be is 2. So that's 2, 3, 4, 5. So 5 is the least possible value of n. Does that make sense to you? You're having to figure out what you know about the zeros and what you know about from the graph and what you know about imaginary. So we can say that least possible, you can abbreviate, value of n is 5. You can't put n equals 5 because we don't know that that's true. It could be 5. There could be other zeros, other imaginary ones they didn't tell us about or something else, but the least possible from what we know right now is 5. Everybody okay with that? Yes? Okay. Is she awake? Yes. Okay. Just making sure. All right. Polynomial inequalities. We're going to look at it graphically today. Tomorrow we're going to look at it algebraically. But this is just a little reminder because we've talked about it, not in inequality notation like this, but we've talked about where's our graph positive and negative. That's what we're looking at. So when we write f of x, we are referring to the y value on the graph of f of x. So if I say f of x is greater than 0, that's like where is the function positive? That means the graph is above the x-axis because that's where your positive y values are, right? If f of x is less than 0, then the graph is below the x-axis because that's when the y's are negative. Easy enough? Now, we have written the intervals. Where's the graph positive? Where is it negative? But again, I didn't ask you in this specific manner, but it's asking you kind of the same thing. First of all, it's asking me, where does f of x equal 0? Well, if it's greater than, it's above, less than, it's below. When it's equal to 0, where is it? On the graph, right? Here, here, and here. So it equals 0 at x equals -3, -1, and 3. That's where it equals 0. Those aren't intervals. That's at an exact point because it only happens at a point. Then we're asked, where is f of x greater than 0? Okay? Greater than 0 is going to be here and here, right? And those are intervals. Where do we start? -3, and I go to what? -1. Do I include either one of those? No. Then I start back over at 3, and I go to infinity. Okay. So, and one thing you might need to do for yourself when we get a little farther into this stuff, when it says f of x is greater than 0, maybe you need to write yourself, that means it's positive. I'm looking for positive, so you don't get lost in the inequality signs or whatever. Okay, so then I want to know where f of x is less than or equal to 0. So that's here, and that's here. Where does it start being less than 0? -infinity, good. And I go to -3. Now, I never include my infinities. Do I include the -3 this time? Yes, because this says less than or equal to, which means we are looking for negative and 0. Both of those work for me, okay? And so make sure you're paying attention to those inequality signs. Then we start back over at -1, and we go to 3. Do I include those? Yes, because I'm including the 0 there. What questions do you have? Anything? All right, so we are going to start, well, we're going to stop here today, and then the second page we're going to do tomorrow.